supposed to cover these.
Yeah.
That would be the advantage of using DFT energies instead of simply.
On top of that, on top of that, there's a multi-configurational feature include the non-dynamic. So, but he hasn't talked about the DFT yet. So
This is illustration of non-dynamic correlation, right?
Yeah, I see. Yeah. Let's go further.
All right. Let's go to the. Now, well, this is simple explanation of multi-configuration of wave function methods, where we develop this idea somewhat further. We split all the orbitals, for example, at the CAS-SCF level, into core orbitals with fixed occupations, and vacant orbitals, also always empty, and active orbitals, where we include some number of occupied and unoccupied orbitals, but we then in the wave function we do all possible excitations from occupied to unoccupied orbitals within the active space, within this subspace of the orbital. So this will lead to quite sometimes to quite long expansion for the wave function, which is quite difficult to interpret. But one of the ways to interpret this wave function would be to use orbital occupation numbers, these fractional occupation numbers. We can obtain from the wave function, we can obtain density matrix, and by diagonalizing it, we can obtain natural orbitals and fractional occupation numbers of the natural orbitals. We can associate with some, let's say, correlations. If we see that in these fractional occupation numbers, if they strongly deviate from 2 or 0, then we can speak about strong non-dynamic correlation. For example, if we have occupation numbers of some orbitals close to 1 and 1, then usually we say that, okay, we have strong non-dynamic correlation where the respective electronic configurations are mixed with nearly equal weights. So that this is, say, just formal illustration of multi-configurational methodologies in the wave function world. Usually they work with quite long expansions, and the size of active space may cover, let's say, maybe 10 or 12 electrons and equal number of active orbitals. So the expansion for the wave function will be pretty long. And it will be quite difficult sometimes to optimize this wave function. But in the end, we hope to obtain accurate description of the non-dynamic correlation, at least. But in reality, CAS-SCF, although this is the simplest of multi-reference methodologies of wave function world, it does not lead to too accurate description if we try to plot different methodologies on these in the two axes, say accuracy on the abscissa and price of the calculation or cost of the calculation on the ordinate axis, then CAS-SCF is pretty cheap compared to other methods. However, its accuracy is not always, let's say, satisfactory for the chemical purposes. CAS-PT2 methodologies, where on top of this multi-configurational wave function, we include some dynamic correlation through perturbational theory. It's, of course, more costly, but gives us better accuracy. Further, we can go to multi-reference CI with single and double excitations, MRS-DCI, where we include single and double excitations on top of the CAS-SCF wave function. Excitations, I mean, from core orbitals to vacant orbitals, not only among active orbitals, but from core to vacant. And of course, on top of everything will be full CI, where we simply expand active space
Yeah. So let me add this. Yeah. For Anna, can you go to the next figure? I like. No.
Yeah. This.
No. Yeah. This figure. So basically, we know the CASA-CF. CASA-CF is good for the non-dynamic correlations. That's we all know. But you need to specify active space, which composed of the limited number of orbitals. So we called it those active orbitals are correlated. Okay. There are a lot more uncorrelated orbitals, like from the deep down occupied orbitals are not really included in the active space. That's where we lost a lot of the dynamic correlation for those. We only recover dynamic as well as the non-dynamic of that active space orbitals mostly. So there are a lot more orbitals that are missing. So non-dynamic mostly comes from few orbitals in the case of non-dynamic. But in the case of dynamic, we need all orbitals. So there's a big difference, okay? So non-dynamic, just a few orbitals are necessary.
Right.
Dynamic, we need all of them. But the CASA-CF recovers non-dynamic very well because that we put the few orbital in the active space, but then it cannot recover all the dynamic correlations because only active space orbitals are correlated. So that's why CASA-CF misses a lot of dynamic correlation, although it almost perfectly recovers non-dynamic correlations, but it misses a lot of dynamic correlations. So in order to recover dynamic on top of CASA-CF, they use a perturbation theory, COS-PT2. So they think that COS-PT2 is really well balanced, almost perfect, as good as you can get, because you have non-dynamic from CASA-CF and dynamic from PT2. So it's a combination of those two looks wonderful, right? That's, I think, their ideal, I mean, kind of a de facto standard these days. But we tested this a lot. We found that this is not good enough. And that's why we need the new theory like Michael's theory and our theory. Our theory overcomes many of the deficiencies. COS-PT2 is good, but it cannot recover well. It's simply because CASA-CF is too bad already. The reference is too bad, so PT2 may not be able to recover all the correlation well. That's the kind of things we observe these days. So really, you need to go to full CI to get the all correlation well, but we cannot do it. So that's why we need to do a completely different path. But still, I mean, if you talk to the people, the quantum chemists, they all consider COS-PT2 is the ultimate answer. That's the final answer for this kind of situations. And that's still the current situation. I mean, that's what they, but we think differently. Okay, so that's exactly what, go ahead.
No, I did not work with COS-PT2 myself, but it also, you need to choose active space, yes?
Right.
Exactly.
Right.
So you need to for special system, you apply your chemical intuition.
Of course.
Largely it's defined by chemical intuition, indeed.
So what I'm trying to say is that even if you have a wonderful chemical intuition, if you start using CASA-CF, it's already too bad to recover the correlation properties. That is our observation. So we'll talk about more about that. But okay, Michael.
All right. Yeah, of course, we then can go to as high as full CI heaven, but the price of this calculation will be extremely high. So we can do it probably for very small molecules. DFT is very cheap. However, its accuracy varies in wide margins. So I probably, it's error bars or error margins here not I didn't show them correctly. It should be from like 0 to infinity quite often. So it's especially it becomes very inaccurate for multi-configurational situations where the non-dynamic correlation becomes very important. So what is the problem with the standard Kohn-Sham DFT? Basically, I can say it right away that this is a single determinant approximation. So how it is usually formulated? So there are two important statements behind standard Kohn-Sham density functional theory. First one is the Hohenberg-Kohn theorem, which says that the ground state energy is uniquely defined by the ground state density, which means that there is one-to-one correspondence between the density and the energy. And for any given density, there is unique ground state energy, and vice versa. Well, of course, from the solution of the Schrödinger equation, we know that we have energy, then we will automatically have from the wave function, we will have its density. But it was what was unusual with this statement, that given the density, we will always have one and the same ground state energy that corresponds to it. So therefore, we can always find this energy. We should be able, better to say, we should be able to find this energy from the known ground state density. Density can be measured experimentally. Therefore, what's important about this theorem that it connects one observable, you know that wave function is not observable, but the density is, with another observable, which is energy. This is a very nice statement, of course, but practically it's very difficult to apply if you don't know energy as functional of the density. Usually you don't know that. As a practical implementation of this statement, of this theorem, Kohn and Sham, they proposed a method where we try to map the exact density onto the non-interacting density of non-interacting particles, which is exactly the same as the density of the interacting particles. This is a little bit tricky statement, which I can illustrate by this simple cartoon. Imagine that we can scale down electron-electron interaction in the Hamiltonian, you know, this 1 over R12 term here, by some coefficient lambda. So if we set lambda equals 1, we will have physical Hamiltonian with fully interacting electrons. Fully interacting electrons moving in some external potential, and they have certain density. I labeled it rho naught here, which follows, the density follows from the wave function from the solution of the Schrödinger equation for this system. So this is physical system. But now imagine that we do the following. We scale down the electron-electron interaction all the way from 1 to 0, and simultaneously we modify the external potential in which these electrons are moving. For example, in the case of atom or a molecule, this will be electron-nuclear attraction potential, right? But we now modify this potential in such a way that the density remains the same along this path. This is adiabatic connection path. And we end up with a system of non-interacting electrons, lambda equals 0 here, which has exactly the same density as the physical system, right? So, I understand this is a tricky concept, but it's adiabatic connection concept is, or adiabatic connection trick is quite often used in solid state, I mean, in many body physics to simplify a description of, let's say, exact many body systems. It will be reduced to some system of non-interacting particles. The main question now is whether such potential, this modified potential, exists or not. And as, oh, sorry. Oh, yes, right. I'm at the right slide. So Answer to this is yes, it does exist, provided that certain conditions are fulfilled along that adiabatic connection path, along that path where we vary the scaling parameter lambda between 0 and between 1 and 0. So these conditions largely boil down to the validity of perturbational theory along the adiabatic connection path. If the perturbational theory, roughly speaking, remains valid along this path, scaling down electron interaction, then the corresponding, let's say, in this case, Kohn-Sham potential, Vs, it exists, and then the energy difference between this and that system will be given by simple thermodynamic integration expression where we take derivative of the total energy with respect to this electron-electron scaling parameter and integrate between 0 and 1. In practice, it's, I don't know, it's probably impossible to apply this equation, but at the formal level, it can be, say, derived, this equation. And it shows that this adiabatic connection path is, in fact, say, some kind of mathematical trick which can be used to justify the Kohn-Sham methodology. So, and in Kohn-Sham methodology, we assume that the density of the non-interacting system, this system, non-interacting quasi-particles, quasi-electrons moving in some kind of modified potential, external potential, Kohn-Sham potential, is given by a single determinant, single-threaded determinant, and that the Kohn-Sham potential, this potential exists. So we cannot prove it for any system, but we simply make these assumptions that is single determinant and it exists. Therefore, we can reformulate the whole problem of solving, say, many electron, or finding the energy of physical system with this density rho node in the following way. So we split off first, we split off contribution from the external potential, real physical external potential. We split it off, and the remaining part we can also separate by using this trick, projection onto the non-interacting system of non-interacting particles. We can separate into the non-interacting kinetic energy, so kinetic energy of these electrons moving in the modified potential, and the rest of the energy. Let's say the rest of the energy we can further split into classical Coulomb repulsion between the electrons with this density and the so-called exchange correlation energy. So in this way, we will obtain the energy of interacting system through solving, say, some kind of many-body problem for non-interacting particles. And for non-interacting particles, it's very easy to solve. In many cases, it's given by a single determinant only. Right. In fact, in practical, say, implementation of this methodology, we use we approximate only the exchange correlation energy here. The classical Coulomb repulsion is known exactly for the given density. Then we obtain the following expression for the modified Kohn-Sham potential as a sum of external potentials. So, for example, electron nuclear attraction potential plus functional derivative of the exchange correlation energy with respect to the density. And we use this potential in a very simple, say, it will be secular equation for the orbitals with kinetic energy plus this external potential as this quasi-Hamiltonian for the non-interacting electrons. From this, we find expansion, we find orbitals, which will give us the exact density, assuming that the solution of this system, non-interacting system, is given by a single determinant only. And from these orbitals, we find the density of the interacting system, because both are supposed to be equal. So it gives us a practical way of implementing the Hohenberg-Kohn statement, Hohenberg-Kohn theorem in practical calculations. However, there is a problem with this methodology, and this problem is exactly with these two assumptions which it is based on. So the main is that the density of non-interacting system is given by a single determinant density. So it can be, in other words, it can be mapped onto a single density of a single Slater determinant. Why is the difficulty? Because the Hohenberg-Kohn theorem, as you remember, oh yeah, here. Hohenberg-Kohn theorem is valid only for the ground states. It was formulated for the ground states only, and it uses variational principle as the main tool to prove the validity of this theorem. Therefore, we need to have density of non-interacting particles also as the ground state density. So it should be ground state density for the interacting particles and ground state density for the non-interacting particles. Then if rho s, non-interacting, can be represented still by a single Slater determinant, we're basically done. That will provide us, say, exact or accurate solution. In practice, of course, we can find exact exchange correlation functional through application of the say adiabatic connection trick, but it's very impractical and say impossible to implement in any practical computational scheme. Usually they are approximated, and within the say accuracy of these approximations, we can obtain the exact energy of the interacting particles. Right? So this is the trick. But behind the trick is a very strong assumption that the density of non-interacting particles is given by a single determinant, which is the ground state of some non-interacting problem with this potential. The question is whether such potential exists, which gives us such density. So it is, in other words, it is V representability problem, non-interacting V representability problem. And in reality, as it was found out first from experience, and then it was formalized by a number of researchers, the assumptions behind Kohn-Sham DFT are not always valid. For many systems, they are probably good assumptions, but for many other systems, they are not. So strictly speaking, Kohn-Sham DFT can be applied only to the ground states. And the existence of the exchange correlation potential, or of the Kohn-Sham potential, is only assumed there. It has never been proved rigorously. And well, there are some other disadvantages of this methodology in practical terms, but these are probably the most important from formal point of view. However, alternative formulation of density functional theory, which uses ensemble representation for the densities, can operate both with ground and excited states, and their existence of the Kohn-Sham potential or exchange correlation potential has been rigorously proved. And this is big advantage of Ensemble DFT before the Kohn-Sham DFT from the formal standpoint, formal point of view. So what is, I very briefly outline what are the ideas behind Ensemble DFT. Basically, it is the same as multi-configurational representation of the wave function in the wave function theory. Only now we operate with densities. So the statement that was proved by many researchers, basically say 40 years ago, it began. Formal statement was that any physical density can be mapped onto ensemble density. Any physical density, fermionic density in this case. That is important because bosons, they don't care about all these tricks. Fermions are very individualistic. They sit in different, they should have all different, say quantum numbers sit in different states. but bosons feel comfortable in the same quantum state. Like if we had orbitals, then all bosons could be sitting in one and the same orbital, no matter how many bosons there would be. But fermions are different. And any physical density of fermions, of electrons, electronic density, can be mapped onto ensemble density. Ensemble density is simply average with some coefficients of densities of components of the ensemble. So this is, so far, this is very formal, formal statement. And exact functional form was derived by Elliott-Leib, so in 1983, and it corresponds to the same expression, formal expression, only with internal energy, or in this case, this will be Helmholtz energy from thermodynamic point of view of electrons, of the, say, ensemble components. Later, in the end of 80s, the concept of ensemble DFT, this was formulated first for the ground state, and later it was extended to the excited state, where variational principle for ensembles of ground and excited states was proved by Gross, Oliveira, and Kohn, in the sense that if we take some weighted sum of energies of several states, ground and several excited states, combine them into one ensemble with fixed weights, then, and variationally optimize it, then this average energy will be always above the average energy of the exact solutions of the Schrödinger equation. Right? So this is the essence of the variational principle. So if we take now these trial wave functions, whatever type, we can say freely optimize them, and we'll never fall below the exact value.
Is that you optimize the coefficients omega here?
No, omega here omega are fixed.
Oh, okay.
Yeah, in this case.
I see.
Well, and this is basis for variational formulation of density functional theory for excited states. It should be not a single state, but several states, ground and some excited states included into the ensemble. And in this way, we can define these energies of individual components variationally. So we can apply the variational theory.
So the omega is a fixed for all states.
Yes, right. Here, omegas are fixed. There, they may be not. Well, formalities have been derived, as I said, in the very important work by Elliott-Leib, where the most important statement was this theorem that essentially proves the validity of these two representations. What's important, the same coefficients. Here we use the same coefficients for components of the ensemble. Right, Elliott-Leib has proven this equation in his important work, and later the existence of the functional and its differentiability was proved by two German scientists with the name English, which doesn't mean English, but let's say angel is angel, say angel. Angel is angel in German, right? So they are two angels.
Angel.
And they have proven differentiability of this density functional, of the ensemble density functional. So
adiabatic connection here, do you?
They did not use adiabatic connections.